Okay, welcome back, ladies and gentlemen. We are moving on to the next part of the topic. So, topic 12 has been Earth's dynamic crust, which we've talked about a little bit so far. Now we're going to get into the interior part of this topic. So, first thing, right, this part of the topic is called the inferred properties of Earth's interior. So, what does the word inferred mean? We looked at it all the way back, probably the first or second day of school, right? And it sounds a lot like inference. And if you remember, an inference is essentially an educated guess, but it's based on some observations. It's not just some random idea. So when we're looking at the interior of Earth, everything that we know about Earth's interior is really inferred because we've never actually been that far deep into the Earth. In fact, if you picture the Earth as a peanut M&M, right, with, the color on the outside part, and then you have the thin candy shell, then you have the chocolate, and then you have the peanut inside, right? We haven't even made it through the color on the outside. That's right, we haven't even made it through that far. We've only gone about 8 to 10 miles down into the Earth, right? And our Earth is, as we're going to see in a little bit, several thousand kilometers deep. All right, so everything that we need to know about Earth's interior, based on what we've inferred, is going to be on page 10 of the reference table. So if you haven't already done so, open up your reference tables. This is page 10. And what I'm going to do is I'm going to take a few moments and I'm going to go through all the different parts of this chart. It looks super, super busy. There's a lot of information on it, but it's actually not that difficult to understand. Essentially, it's broken down. If you start here on the bottom, this is a graph that shows depth and temperature. Then you move up here to the middle. This is another graph. It shows depth, the scale is just down here, and the pressure. This top part is probably the busiest, right? This shows us the different layers of the Earth, all the way from the inner core, outer core, stiffer mantle, the asthenosphere, plastic mantle, the rigid mantle, the crust, all right? It also shows us the different densities of these layers. So let's take a look at each of these things. So what does this table actually show us? So first thing it's going to show us is the depth. So all the way down here on the bottom of the chart, it shows the depth. So what I'm going to do is I'm just going to zoom in a little bit more so we can see it. Right? Our depth goes from right here, right? This would be Earth's surface. All right, I apologize, handwriting is terrible, but that should be the word surface. All right, so this is Earth's surface, and then all the way down here, right, this is 6,000 kilometers. I would say that this is about 6,500 kilometers, and this would be essentially Earth's center. Okay, so if you were to dig a hole in your backyard, which you can't do by the way, and dig yourself all the way down to the center of the Earth, it would be about 6,500 kilometers deep. Right? That's pretty deep. All right. Next, if we stay on that bottom graph, the second thing that it shows us is the different temperatures. All right. And it is a graph. So when we look at this, all right, and again, I'm going to zoom in just so we can see it a little bit better. All right. As our depth goes from 0 to 6,000, what happens to our temperature? Well, our temperature is going to rise, and then it's going to get also to a temperature of, I'd say, about 6,700 degrees Celsius. So the deeper you go inside the Earth, the hotter it is going to get. And that should make sense. More pressure, greater temperature. All right, remember I just said that. Jumping back. The next thing it shows us is now our pressure. Right now, this is not air pressure. This is the pressure of the rocks sitting on top of you, and it's measured in millions of atmospheres. Not just atmospheres, millions of atmospheres. So now, if we take a look over here, we have pressure on the left. Our depth scale stays the same. Notice, right, these lines line up. So your 0 goes, this is also 0. Come down here to 1,000 kilometers of depth. This is 1,000 kilometers of depth. Here is 2,000, 3,000, 4,000, 5,000, 6,000, all the way up to about 6,500. Now, what do you notice about the pressure when you compare it to depth? Well, we start off here at 0, and then as we go deeper inside of the Earth, the pressure is going to increase. If you were to go down to the center of the Earth, it would feel like you had about 3.5 million atmospheres above us. What does that mean? Well, right now, we have 1 atmosphere above us. That's the pressure that's pushing down on us. If you go deeper into the Earth, you're going to have more material on top of you, and that would equal that amount of pressure. The center of the Earth has about 3.5 million atmospheres worth of pressure. All right? Meaning you would be squashed like a little bug. Next, all right, we're going to jump up to the top right-hand side where it shows us the density, right? It shows us the density of all of the different layers of the Earth. Now, I know we didn't talk about the layers yet, but here they are, all right? Inner core, outer core, the stiffer mantle, all right? The asthenosphere, the plastic mantle, the rigid mantle, and the crust. It's all right here. And again, I'm just going to zoom in so we can see it a little bit better, all right? Now, this shows us that our densities are different with each layer. We are most dense near the center of the Earth, and our density decreases as we go up to the top. But notice, remember when we talked about igneous rocks and we mentioned that there were 2 different types of crust? I brought this up. All right, we have basaltic oceanic crust, right? And then we have granitic continental crust. So our continental crust is made of granite and has a density of 2.7. Our basaltic crust has a density of 3.0, right? These are your mafic basaltic rocks. Here is your granitic felsic rocks. What does that mean? Well, remember when we talked about the convergent plate boundary, which can be seen on your reference tables, page 5? Well, when you have a continental crust colliding, converging, or coming together with oceanic crust, which one did we say was going to override or go on top? The continental crust. Why? Here we go, less dense. Okay, so this chart shows us density, Right, next, it's going to show us the layers of the Earth, right? And there are several different layers of the Earth. We're going to get more into that in a little bit more, or in a few minutes. So again, you have your inner core, your outer core, your stiffer mantle, your asthenosphere, which sometimes is known as the plastic mantle. Then you have your rigid mantle and your crust, which when you combine them becomes the lithosphere. And then for those of you who don't remember, the word lithos was the Greek word for rock. So the crust and the rigid mantle is going to be made up of lithos, meaning rock, hence the lithosphere. All right. The sixth and final thing that this chart actually shows us are 2 plate boundaries. All right. So I'm going to zoom in so we can see them a little bit better, but we'll start with the mid-Atlantic ridge. The mid-Atlantic ridge shows us that the asthenosphere, the magma inside here, is pushing up, pushing these 2 plates apart. What type of boundary is at the mid-Atlantic ridge? That is a divergent boundary. So this is what it looks like. We come over here, right? Now, this is the western coast of North America. How do I know that? Here is North America. Here is the east coast. This is the Atlantic Ocean. This is the west coast. This is the Pacific Ocean, right? So right along there, we see this plate moving this way, right? And this plate moving this way, with the oceanic plate going underneath, going down beneath the continental plate. This is a convergent plate boundary. Also, how do we know that? Here is the word trench. So if we look, what is the name of every single convergent plate boundary? So I'm just going to jump in the reference tables to page 5 so we can see it. Oh, too far. Right, so here is page 5, right? Our convergent boundary, over the arrows point together. Remember, here is our convergent boundary. All right, so trench. Convergent boundary, the Aleutian Trench. Convergent boundary, the Mariana Trench. Convergent boundary, the Tonga Trench. So every time that you have a convergent boundary, you're going to have a trench. And in case you didn't know what a trench looked like, this is a really good side view of a convergent boundary showing you what that trench is going to look like. So there is that trench, this small V in here, because the oceanic plate is going down, creating a trench or a hole. All right, so those are the 6 main things that are shown on this graph. Now, let's break it down a little bit more. Let's take a look at the layers, right? And there are four main layers. We're going to start from the outer part and we're going to work our way in. So all the way up, right on the top here, if we follow this line, right, the outermost part of the Earth is going to be the crust. Okay? The crust, that's the part that we live on. All right? That, again, think back to that peanut M&M. That's that thin color coating on the top, not the candy, the coloring on the top. That is the crust. Now let's work our way underneath it. Underneath the crust here is this kind of white area, which is the rigid mantle. All right. The word rigid means stiff or hard. Now we have mantle. Now I got a little ahead of myself, right? Because you notice this says rigid mantle, the asthenosphere plastic mantle, and then we have stiffer mantle. So these three parts here are actually considered the mantle, right? But the mantle is actually broken down into three different sublayers, and we got the first one already, right? The first one is the rigid mantle. Again, the rigid mantle, right? When we combine that together with the crust becomes the lithosphere, right? Again, the rigid mantle and the crust becomes the lithosphere. So this area here is the solid outer part of the Earth, right? The crust is the coloring, right? And then we have that thin candy shell part, right? The rigid mantle would be essentially part of that, right? That's our bedrock. Next, we have the asthenosphere, which is also known as the plastic mantle. Now, when we look at this, right, notice that you have all these arrows moving around inside of the asthenosphere or the plastic mantle. This area here is where we have magma, right? This magma is what actually causes these continental plates to move, or if you remember from earlier in the topic, continental drift, right? And plate tectonics. This idea is because the asthenosphere is one very, very hot area where rocks have melted, magma is moving around, and we see convection currents. And it is convection that is moving these plates. All right, underneath that we have the stiffer mantle. Right, here's the stiffer mantle. Now, what is the stiffer mantle? Well, the stiffer mantle is going to be, the word stiffer means hard. So this stiffer here, this is no longer plastic. So this is flexible and there's movement. There is no movement in the stiffer mantle. This becomes solid again, much, much, much harder. All right. Then we have the outer core. Right? And here is the outer core, and just to point it out, our outer core is composed of iron and nickel. Right? We're going to come back to the outer core in a moment. Right? Then we have the inner core. Right? So those are our four main layers. All right? Starting on the surface, we have the crust, then we have the mantle. Mantle is broken down into three different parts: the rigid mantle, the asthenosphere, plastic mantle, the stiffer mantle, the outer core, and the inner core. Now, before I go any further, there is one more thing. Right? See this word MOHO over here? Right? It's actually an abbreviation, right? And what it is known for, the MOHO is the boundary between the crust and the mantle. All right. So yes, there is a difference between the crust and the rigid mantle, right? That is what is known as the MOHO boundary. All right. So just add this here, right? Boundary between crust and mantle. Add that to your reference tables, right where it says MOHO. Right. Make sure you have that. Okay. So before we even get into the questions, I just want to take a look at this chart to make sure that we fully understand it, because I said everything goes together. So let's say I want to know what the pressure is at the boundary between the outer core and the stiffer mantle. Well, what do? This shows me the boundaries. This here, this line is the boundary or the interface between the stiffer mantle and the outer core. Just follow this down. See this dashed line? This dashed line marks off where that boundary is. Same thing with this one over here and these two. So this is the boundary between the two. So if I wanted to know what is the pressure at the boundary between the stiffer mantle and the outer core, I find that boundary and I follow it down to here. Right, I get to this point. Right, now I want the pressure, so I'm going to hang a left, go over this way, and I'm about 1.5 million atmospheres. And it would work the same way if I wanted to know the temperature. Go down to the bottom, right? Follow that dashed line. So the temperature at the boundary between the stiffer mantle and the outer core, again, here is that point. Now hang a left, 5,000 degrees Celsius. So there is a very, very high temperature. All right, so that's how these three parts work together. Now, the last thing that I want to do on this before we go and answer the questions is I want to take a look at the different layers, and I want to break them down into whether or not they are a solid or a liquid. And now the way that we see that is based on this temperature line. Okay, see these dashed lines, that the small dashed lines that run through, that's the melting point. Now, if something reaches the melting point, that means that it's hit a temperature where it will melt. So think about it this way. If you had an ice cube in the freezer, is that ice cube going to melt? No, because the temperature is below the melting point. If you take the ice cube out of the freezer, the temperature is going to go up, so the temperature becomes higher than the melting point, and the ice starts to melt and becomes liquid water. So when we look at the different layers of the Earth, we can determine whether or not it is a solid or a liquid based on its melting point. So if we take a look at the inner core, so this area here, all right, our melting point is higher than the actual temperature. So since the temperature is less than the melting point, this is going to be a solid. Right? Now if we move over to the outer core, so now we're in this area. So now the temperature is above the melting point. So since our temperature is above the melting point, what does that tell us? Are we a solid anymore? No, we are a liquid. All right, we are a liquid. All right, now let's jump to the stiffer mantle. All right, let's jump to the stiffer mantle. All right, come down to the temperature. Here is our melting point. Here is our temperature. So the melting point is above the actual temperature. What does that make this? Solid. Right? And now the last part, the asthenosphere. The asthenosphere is known as the plastic mantle. Right? Remember, plastic. So in this case, we're in this area here, the temperature is just a little bit above, and it even tells you that this is partial melting, right? So this is also going to be a liquid. There's going to be some solid in there. That's the bottom of the plates that float on the asthenosphere, right? So if we go all the way up, here are the plates that are floating on the asthenosphere, the plastic mantle, and it allows it to move around. Okay, so again, inner core, solid, outer core, liquid. Stiffer mantle, remember stiffer, solid. Asthenosphere, plastic mantle, liquid. And then of course the crust, the part that we walk on, has to be solid. Okay, so that breaks down that. So let's take a look at some of the questions. All right, so what is the pressure at the deepest part of the stiffer mantle? Okay, so here's the deepest part right here, right? And the pressure, we answered that a moment ago. We go to this point, and now we're going to hang a left, right about there in the middle. So the pressure is going to be about 1.4, 1.5 million atmospheres. Okay? Next, what is the actual temperature of the boundary between the inner and outer core? So I want the temperature between the inner and outer core boundary. So jump to this. All right, here is the outer core, here is the inner core, this is the boundary, and I want the temperature. So we're going to come down to right there, right about this point, and we're going to go straight over because I want the temperature. I know, I'm sorry, my line is not straight. Right, we are a little bit above 6,000. I would estimate it to be about 6,000, let's say 300. If you said 6,200, 6,400 degrees Celsius, you are close enough, right? You have to be close, not perfect. Okay, number three, what is the layer of the Earth that the tectonic plates move on? So remember, Earth's tectonic plates are up here. That's the crust and the rigid mantle. So what allows those plates to move or float on? All right, well, that is going to be the asthenosphere or the plastic mantle. Remember, that is semi-solid, not totally liquid. It's a plastic, but there is movement. All right. 4. What is the density of the continental crust? Again, don't have to memorize this. Right up top, density, we have a whole thing right here. The density is going to be 2.7, again, right up there, 2.7 grams per centimeter cubed. And now, finally, number 5. Why is the continental crust thicker than the oceanic crust? Well, why does that happen? Because the oceanic crust is going to be more dense. So it's actually going to sink deeper into the asthenosphere. And the bottom part is going to melt. So since it is more dense, it's going to sink down, forcing it down deeper into the mantle, that asthenosphere, where it melts, and you don't have as much solid material. So your continental crust, because it is less dense, is going to float higher, and there's going to be more of it. Okay, now that takes us to the end of this part of the topic. So if you have any questions, please reach out to me on Teams or send me a message and I will gladly explain it, especially if you have any questions on the reference tables.